Hi friends, a very good morning. In the last few videos we saw how to create a Pytorch pipeline for classifying whether an image contains malignant or not, right? In this video we're gonna do something slightly different and very important for proceeding further. So we are going to convert refactor our code in a way that we can use a powerful framework and kind of a new framework called Pytorch Lightning. Why we are doing it is to take advantage of some of the modern hardware and some of the techniques like gradient accumulation that we can use when we want to train images of larger sizes. Okay, why larger size training is difficult with the existing PyTorch code? It's still possible that we can train with the PyTorch code. Anything and everything that we do in PyTorch Lightning is quite possible with PyTorch, but it's our code base starts becoming more and more complex, right? So PyTorch Lightning, what they do is they kind of take care of a lot of engineering work from us, like they make it easy to use FP16 half precisions, and logging is made much easier, right? You can have it run on multiple GPUs. There are a lot of things that you can make it easier. You can quickly look at PyTorch Lightning, what are some of the advantages that you get, right? But in this video we'll focus on converting our code into PyTorch Lightning, okay, so that we can run it using half precision. We can try gradient accumulation and probably a few other tricks, right? How do we do that? We're gonna build it mostly from scratch, except for some part. I've already opened a Visual Studio editor. Okay, we are not doing it in Jupyter Notebook, just for a change. I started falling in love with Visual Studio for last more than a year now, so I thought I'll show you how I end up using Visual Studio. Okay, so I've created a folder called lightning demo, okay, and I've created some of the files. One is augmentation.py. What does it contain? The same augmentation code that we have seen, which returns train transforms and test transforms, two transformations. One is for the training and one is for the test. And I have a data.py file which contains the two important things. One is how the logic of how to split the train and validation data from the given data, and we also see how to create a melanoma dataset, which is a simple PyTorch dataset. All it does is it gives us an image with a target variable, okay, after applying the transformations that we want from the augmentations library, right? And then a very important file as of now, lightning.py, which is going to contain our core code, which is empty, which we are going to do it from the scratch. So I'm going to show you from the scratch, but I've been using Lightning for the last 1 to 2 months, so I've been slightly comfortable. So there is a very high chance I could be making some errors. And if you're new to Lightning and PyTorch, you will learn some of the tricks. If you're already, probably you can fast forward the things which you already know. Okay, and the model.py, it all contains the same code. It's just refactoring of our existing PyTorch code. Okay. We have, so I have taken only few things from here. We have not taken things like the training step, validation step, get the train later, data loader. There is no fit function. We are not going to use this. There are some parts of the code which we believe that is useful from the code that we have written. Okay, and we'll start from there. Okay, the first important thing, as most of you would have guessed, is import the PyTorch Lightning library. Okay, it's imported as PL. I think that's one common practice. I've seen some people doing it. Let's define a class. Okay, let's call it melanoma classifier, because that's what we are doing it here. It can be any name. Okay, and we have to subclass something called PyTorch lightning module. Okay, and it's gonna have in the default initialization method, and let's not forget to call the super, otherwise Python may not like it. Python will not like it for sure. Okay, let's create the model first. Okay, before we create the model, let's import it. Let's say from, sorry, it's model import melanoma efficient. That's what we called it. Okay, melanoma efficient. Okay, model name is equal to, let's say, model name, and let's initialize it here. Let's just go to the model and just do a copy paste, which is much more faster. Okay, a couple of things we would need. We will just import it whenever we need it, right? And then let's start with something very simple. Just like how our Pytorch model, right, contains a forward, this also Pytorch Lightning module also contains a forward. Okay, since we already have a Pytorch model, so what we are gonna do is whatever input we get, let's pass it through our model. Okay, so nothing fancy here. Okay, I think there's some error here, is not defined. Okay, this should not be here, it should be here. Okay, so now there are much more things that we have to do here, but before doing that, let's try to run the program. Okay, and Pytorch Lightning is going to throw some errors, and let's try to see what are the errors and how do we fix that. Okay, the entry point of the Lightning program is something called trainer. Okay, and how do you create it? pl.trainer. Okay, we can have it empty for now. We'll add few things to that, and every trainer comes up with the important function called fit. Okay, where we have to pass a Lightning class object. Okay, Melonama classifier. Okay, now what we do is let's try to run and let Pytorch Lightning throw some errors. Okay, it throws a couple of errors, out of which the key errors is it says it needs minimum a training step, a training data loader, and configure optimizer. Okay, so for all of these we need the data, right? For data we need a path to load it from. So let's say path. In my case, I know where is the path. It is just one step behind my existing directory, and I've stored it in 256. Okay, we will need pandas data frame to read it. Import pandas as PD. Okay, let's store the path because we'll be using this path at multiple places, and I want to store it as a pathlib object. So for that, what we'll do, from pathlib import path, and then say path has to be capital path of the path whichever we pass from the class argument, right? And then let's say df equal to pd.read csv. We are reading a csv file, and say self.path slash, we know it's in train.csv. Since I've already done this, I know where the paths are. If you're trying it for the first time, don't worry too much. Okay, so now what we're going to do is we're going to divide this into train df and val df, right? That's what we did in earlier Pytorch code. How do we do that? We have written this function called get train val split, something similar to that. Well, let's import that, and while importing it, let's also import the Melonama dataset because we would need it in some time. And let's also import a couple of other important functions like datasets. We don't need dataset, we need the data loader. Okay, and let's just call the function here and then say df. Okay, so we have train df, and we need to pass the augmentation, right? We need to apply some kind of transformations, which we have already written from augmentation import get augmentations. Okay, so here what we are going to do is self dot augmentation equal to get augmentations, and that's actually wrong. That's don't how we call it, right? The reason is we get actually two kinds of train transformations. Again, we can call it that way, but let's not do it. Let's call it this way: self dot val tfms. If you have called it that way, then we could have accessed it as if it's a list. Okay, so now we have we have read the data frame. We've read the CSV file as a data pandas data frame. We have split that into train data frame and validation data frame, and we have augmentations to apply. Now we know that we need a train data loader. Okay, so let's create a train data loader. Okay, the advantage of using Visual Studio Code, right? You end up getting all the recommendations from Visual Studio and what could be train data loader, right? So what is the first thing that we're going to do is we create a data set. Data set is equal to, no, it's a Melonama. We have done some customization to the existing Pytorch data set. Okay, the first input is data frame. Let's say df is equal to self dot train df. Okay, and then you need the im path, which is basically where the images are. It's, we know, self dot path. Okay, inside that there is a folder called train for the train data loader, and for test it's test. Okay, and then we have to pass transforms. Okay, we have to pass train transforms, right? So it is train transforms. Okay, all set to go. We have a data set. Now let's create a data loader. Okay, what do we need for a data loader? We need a data set is equal to data set, and then what else we need? We need shuffle. For train, always keep it as true, and then num workers, by default it uses only one worker. Let's say we want to use 4 workers. And what else we need? I think we're good. I think we should be good. Okay, I forgot a key thing. It's called batch size. Okay, I don't think we have initialized batch size, but let's go quickly initialize batch size. I'll just copy this. Okay, and let's put it here. And there's a very high chance when you actually want to run it on larger size, you won't have batch size an argument. So let's say batch size is equal to, for 256, we should be easily able to use a batch size of 64. Okay, now the data loader is ready. Now what you do, you say return train data loader. Okay, the data loader is done. Training step, right? So when I started, I did not know what has to go into a training data step. Either you can look at Pytorch Lightning documentation, or you can be slightly lazy like me. There's nothing wrong. There are 2 different ways of doing things, multiple ways of doing things, right? Just look at when you click on this Lightning module, Visual Studio opens the source code of that, and Pytorch Lightning has got this amazing documentation which shows you an example of how does the training step looks like. Okay, so we know that there is going to be a batch which contains a batch from the data loader that we have created, and a batch index telling what batch exactly it is. Okay, so let's create our training step. And if training step, okay, I want to use hints today, so let me remove it. Let's keep the demo sample. Okay, so basically what the hints tells you is what does the method return, right? It expects a dictionary or integer, basically a lost value. Okay, let's not worry about that for now. Okay, Visual Studio says it's args. Let's have simply batch and batch index, or what we can do is just copy this thing and paste it here. It's very hard to remember all these things, right? So it's a good idea to take advantage of the Visual Studio editor or any IDE that you use. Okay, now let's try to extract the images and the targets from our batch. Okay, so we got the batch of images and targets. Now what do? We pass it through the model, right? Let's call it output, and let's say self of, you can either say self or you can say self.model, because since it's a Pytorch Lightning module, when you say directly self, it calls the forward code. Okay, to save few strokes you can just say self of images. Okay, and then you want to do the last, right? So we have not defined the last. So one thing you can do is, okay, I think we have not imported even if, right? Sorry, import tosh dot nn dot functional as f. Okay, and you can say f dot binary cross entropy with logits, and you can say output comma targets, right? This is one way of doing it. Or what you can do is, let's just copy this for a moment and say self dot last function. Why you want to do it this way? There's a high chance that before the competition ends, you may want to try different things like focal loss. You may want to try label smoothing, or you may want to try a very different loss, right? So every time you don't want to change your training step, or we'll be using the loss function at multiple places, you don't want to change it, right? So what we will do is we'll initialize it here, self dot loss function is equal to here. This you can actually pass it as an argument so that it becomes as a configurable one. Now we have calculated the loss. Now what do you do? We have to just return the loss. We don't need to do anything. Now we can just say like this, dictionary, have it a keyword, so it becomes a bit easier for logging. Okay, so if you see some of the key things, right, in when we did it in Pytorch, pure Pytorch, our training step would have actually looked slightly more complicated, or not complicated exactly, more number of words, right? For example, we have to put each batch to GPU or CPU, then we have to call the op.0grad, we have to a loss function, we still have loss.backward step, scheduler.step, then we have to do a loss.item. When we use Pytorch Lightning, the Pytorch Lightning takes care of all these things, so we can just focus on the logic. Okay, so now we have training step and training data loader. Now what else is missing? Configure optimizers is missing, right? Which is basically a place where you configure your optimizer and scheduler. Okay, like cosine annealing, the one which we used in the kernel script, Kaggle kernel script. If you want to configure it here, you can do it. But to keep life simple, let's just configure the optimizer. Okay, to import optimizer, we need two things. Actually, okay, we have imported this torch.optimizer. What did we import? Okay, actually we did not import it. I have installed a new plugin called Pylance in Visual Studio Code. I'm still not used to it, but that has been helping in auto imports of some of the classes. Okay, let's say optim dot, we used AdamW, right? And here what are we going to do? First thing is we're going to pass the parameters, right? Either we can say self.model.parameters or self.parameters if you're lazy like me, and then say self.lr. Actually we have not initialized lr, that's fine, we'll initialize it in a moment. Self.weight dk, these are a couple of things that you want to initialize. Weight dk. Okay, let's see if this one looks like there's some kind of error. Okay, let's say parameters. Okay, it's not self.weight dk, it's weight dk is equal to self.weight dk. I did it the reverse way. Okay, fine. So what we'll do is we need the self.lr and self.weight dk. Let's copy this and let's put it here. Okay, let's remove this part, let's put it here and say lr weight gk. Okay, and let's initialize it. LR equal to, let's say 1e minus 4. 1e minus 4 mostly works. Wait, we can play with these parameters later. So there's something called learning rate finder. Pytorch Lightning comes with a learning rate finder, though I've not used it. Probably we try to use it one day, and if required, we'll take a small video out of that if it's slightly difficult to use it. But I doubt, since I've been using Pytorch Lightning for quite some time, I find it very intuitive and very easy. So you may find it very easy to do it, right? So let's go to the optimizer. We have called the optimizer. So what do? We say return off. Okay, we don't just say optimizer, it may not like it. We say that we want to return a list of optimizer. Okay, it should be a list of optimizer. The reason is there can be multiple optimizers you may want to use, right? And you may want to have a scheduler also. So now before running it, right now this time it will run. So if we want to pass a couple of things, first thing is we don't want it to run on a CPU. All you want to tell Pytorch Lightning to make it run on a GPU is say GPU is equal to 1, or if you have multiple GPUs you have to say -1, and then you can say distribution parameter what it is. I think, okay, let's not get into the distribution part right now. It's pretty simple. Let's say in my case I have one GPU on the machine running. Okay, then what else you want to do? You want to say maximum epochs, how many epochs you want to run. Let's say in this case 2. Okay, since it's a live demo, I mean I don't want to make you guys wait for the entire code to run, or even when you're trying to build it, right? You don't, before you finish it, you don't want to the code to run on the entire data, right? And Pytorch Lightning makes it really easy by just adding this parameter called argument called train%check. You tell how much small percentage of data you want to actually run the entire code on. Okay, and that's good enough. Now say play, run the code. Let's close this so that you'll have more space. Okay, there's some problem. Okay, here I don't need to say parameters. What is this argument called? It's called params, it's not parameters, my mistake. Params equal to, okay, now run it again. Okay, it's going to run. Okay, there's nothing fancy, right? We're not logging anything, it ran quickly, so we know that the complete code is working as such. But in deep learning we know that there can be a lot of bugs which can go unnoticed, right? So other key important thing, once we know the training step is done or the training part of the model is done, you want to have a validation part also, right? So first thing we need is a validation data loader, then we need a validation step, and then we want to have the metric calculated on the validation data. So we need some 3 kinds of functions. We know for validation loader we can call something like a val loader, validation step, training step, validation step. It's going to be something called validation step, and the third one, it's something called validation epoch end. Okay, so you don't need to remember all these things when you actually do it in Visual Studio, or you can look at documentation, or you can quickly look at here and see some of the functions that you may actually be interested in doing it, right? There's a training step here, there is a training epoch end, so that means there's something called validation epoch end, right? There are a lot of things that you can quickly look at it. In this case we don't need to do it. It's called we need to create a validation data loader, right? It's called val data loader. Okay, let's remove this as usual. It's called hints and it's very useful while coding. You may, I would recommend you to start using it. Even I wanted to use it from quite some time, but I still not have made it as a practice. Okay, so what we'll do is we'll not write everything. Let's just copy this and just refactor the code. Okay, we don't want it to be train df, we want it to be a val df. Okay, image path doesn't change, and this you don't want to apply any random transformations, right? Really, we don't have this. What did I store it as? Okay, I've stored it as this. Okay, then fine, let's use that itself. That's called val tfms. The transforms which just applies to tensor and normalize. Okay, and shuffle we want it to be false. We don't want shuffle. For validation, right, we can have an increased batch size for faster thing. The simple reason is we don't need to calculate the gradients for validation. If you remember, when we actually did the validation step, we have to say with torch.noGrad, we have to tell Pytorch not to calculate the gradients. If it's not calculating the gradients, that means at any given point of time, it needs just half the memory of what it actually required, right? So to make a validation quicker, you can make it into a multiple of 2. Sometimes with a larger model, you can actually make it a multiple of 3 or 4. If it's a larger model and if your validation is taking quite long, you can just try this trick quickly. Okay, and let's change this to, let's not use train, let's call it validate loader. So now we have this validate loader, right? So now we need a validation step, right? Let's call it, we don't require it. There's a function called validation step which we need to use. Okay, let's remove this as usual, and we're going to get the same arguments. Let's put this here. Okay, and most of it is going to be same, so let's copy and paste this. Okay, I was expecting VS Code to do that for me. Okay, but there's some difference from the training step and the validation step. Like what? We want to calculate the metric, the ROC score on the validation data, right? So on each step, we have to capture the output, what the model has predicted, and what the real targets are, right? So let's capture that here. Let's say validation targets are your actual targets, simple, and then we want to pass validation outputs, right? Here what we're going to do is we're going to say torch dot sigmoid of, I hope I've imported torch. Okay, so let's go and quickly say import torch. Okay, let's come to validation step, torch.sigmoid of, you want to pass the output to it. Okay, why we are doing this? When we apply a loss function, the binary cross entropy by default applies the sigmoid or variant of that, right? But when you want to apply a metric, before you apply a metric, you want to apply sigmoid function on top of that. I think validation step we are good to go. Then we want to calculate the metric, right? Before we calculate the metric, let's import the metric itself. It should be in a package called sklearn dot metrics. Import ROC underscore AUC score. Okay, and then go to validation epoch end. Okay, we have not still returned that function itself, right? Def validation epoch end, and as usual, let's remove all these. Oh, I think something went wrong. Okay, it says, okay, it says the outputs can be of these types. Okay, first we know that it's a dictionary of lists. That's what we are passing it here. It is going to have a it's actually going to be a list of dictionary. Each dictionary is going to contain all the keys that we passed in the validation step for each step. That's what it's going to contain. Okay, so if you really want to understand what is happening here, what we'll do is we'll say pass, and let's say debug here, and say debug. I hope it should run Python file. Okay, let's wait for a minute. Okay, so we got here outputs, right? So what does output contains for each step? So here I think it ran 2 steps. Okay, it's a list actually. Okay, and in each dictionary you have loss, val targets, and val outputs. This is what we have. Okay, so what we have to do is we have to accumulate all the losses, val targets, and val outputs in separate tensors or arrays, and then pass it to the evaluation metric. Okay, let's kill the debugging. This is a very important tool. If you have not done debugging, which I see most of the people in data science who start data science may not do it because they would have learned data science in Jupyter Notebook, but this is a very important trick which I would strongly recommend you getting comfortable with. Okay, so now we know what does output contains, right? It just contains these keys. Let's just to make a difference, right? And let me call it val loss. You can just call it anything you want. Okay, then let's say val loss equal to, what do you want to do? You want to take all the losses from the each step and sum it and then divide it by the length of, basically you want to take an average of the entire losses, right? So I'm using for, let's say, some object in outputs. Okay, that's what we get it, and say O of what it's only, we are going to access the val loss that we are going to get from each step, and say length of outputs. So we should be getting val loss. Then we want to get, let's say, val targets. Okay, because we want to calculate it on the, we want to calculate the metric, right? So what we're going to do, I'm not sure. So let's say it's a list, right? Let's write a list comprehension for O in outputs. Okay, and then say O of, what do you want? We want val targets here. Let's put it here. Okay, and now we have a list of multiple tensors, right? So let's do something called torch dot cat. I think it should be there. Okay, I think it's okay. So this by default, if it's running on a GPU, which most of the times, right, we want to copy it to a CPU by calling CPU, and I'm not sure if sklearn would work on a Pytorch tensor, so I'm just converting it into a NumPy array. And probably you guys can check it if it really works on a torch tensor. Sometimes some of the things works. Okay, let's not do this again. Let's just copy this and paste it, and let's remove the space. And it's not val targets here, it should be val outputs. Okay, now we have almost everything. Let's calculate the ROC score. ROCAC score. I would say be comfortable, so be careful with what you pass to this. You have to pass the y true as the first argument and y score as the second argument. If you pass it the other way around, then you get errors. Okay, what is y true gonna be? It's gonna be val targets, right? And what is y score gonna be? It's gonna be our val outputs. Okay, now we have all these things. We want to log all these things, and it's very simple. Create a dictionary called log. You can create a dictionary with anything you want, but let's call it log. And let's say we want val loss to be captured, right? Let's say val loss, and then say val targets. No, we don't need actually val targets. What we need is ROC score, which is ROC score. Since it's validation data set, let's call it val underscore ROC score, and return the log. Okay, so specific way we are returning it, just try to stick to it. The reason is at the end of this video, right, one thing we'll be doing is we will try to look all these logs in an amazing tool called WANDB. So what happens most of the times is you want to run these programs on AWS or GCP or some cloud provider or on your remote mission, okay, and you don't want to look at your command line terminal for what is happening to your metric, right? It will be very nice if you can look at the metric on your mobile phone or your iPad or any device or on your laptop, even though when the terminal is disconnected, right? So WANDB helps you to do that, and I actually started loving that tool. So I'll show you how easy it is to actually do that. Okay, now we have this validation data loader, validation epoch and validation step. Now let's see if it works. That's a key thing, right? Since we said forgive this errors that you see here. I've replaced my graphic card, but I've not updated the software, so it throws some error. So one of the biggest nightmare for a lot of deep learning researchers is to update your software on particularly the NVIDIA software on your mission, because when you try to do it, you miss a lot of things, right? So probably I'll do it one day, right? So it's running, right? So the other couple of things that you want to do apart from these common things, right? Like you want to, let's say, use mixed precision, because this particular GPU is a 2080 Ti, which comes with FP16. Okay, it supports FP16 mixed precision. So how do you do that? Okay, it's actually very easy. If you're using the latest version of Pytorch, that is 1.6, which got released few days back. Okay, or if you're using a nightly version, or you can use an Apex, which is slightly tricky, but it generally slightly faster than the native version available. Let's not worry about it. How to use a FP16? All you say is this, say precision is equal to 16, and you're all set to go. Okay, now your model runs probably 2 to 3x faster. It depends on the model and other aspects to it. Okay, then what do you want to do? Let's say your batch size in this case is 64, right? When you try a larger image, let's say size let's say 512, 512, you'll not be able to fit in a batch size of 64. So you would end up using something of size, let's say 16 or 8 or something, right? So you want to do something called for every bunch of batches. Let's say, for example, for every 10th batch, you want to accumulate, you want to do the actual backpropagation. You want to calculate the gradients for every batch, but you don't want to backpropagate. That's what is gradient accumulation is called. It's a very simple concept. So just for, if you do not know about what is a gradient accumulation, we'll look at it in a different video. It's very simple. In Pytorch Lightning, how to do that? You have to do it like accumulate grad batches and say for how many batches you want to backpropagate. Let's say here I want to say 4 batches. Okay, so this is all you have to do here. And then let's say you want to experiment with a couple of things. Of course, we can use the argparse, Python argparse to configure it as a command line. We'll probably do it on another video if you guys want it. So now you can change whatever you want. If you want the model here, you can change it, batch size, blah blah blah. You can keep changing him. The other thing that I was talking about is the logger, right? I want to visually see what is happening here. So how do we do it? It's going to be pretty complicated. No, actually I was kind of lying. It's going to be very, very, very simple. In fact, first time when I tried it, I was surprised how simple it was. I was just thinking, oh, that's it. Okay, so we call something called WAN-DB logger. Okay, I would say go and look at the website. What is WAN-DB? It's an amazing company. It's called Weights and Biases. Okay, and they have a central dashboard. So I tell my friends and I tell my clients. So one of the common meme that you may face for people working in deep learning, what did you do a whole day or whole week? I tried multiple experiments, but the metric did not increase. For the clients or for your team managers or even for yourself, after a few days, you don't know, right? So WAN-DB helps you to centrally monitor all these reports, and when you actually share some work with your clients or with yourself, after a few days, you can compare with multiple experiments that you have run, right? So, and Pytorch Lightning and WAN-DB works really well with each other. So we have made the first step of importing it. Now let's initialize it. How do we initialize it? Here we call some object name called WAN-DB and then say WAN-DB logger, and you have to pass 2 important names. One is the name of the experiment that you're trying to do. Let's call it Lightning demo. Okay, and there's something called project, okay, which is going to be, let's call it Melanoma Lightning. Call it whatever you want. Okay, you need to have an account though. For the first time when you run, it's going to ask you, do you want to visualize it? Some basic instruction, and you have to pass in a code on your mission. Once you do it, it's going to work very smoothly. And how do you tell Pytorch Lightning that it has to use this? there is something called loggers. Okay, you pass in a list of loggers that you want. In this case, we are passing a something called vandb. Okay, I think I forgot the comma here. Okay, so now what happens? So now to look at things, right? Let's say we run it on 20% of the data, and let's see what happens. Okay, I don't want accumulate batches to be 4 because right now the batch size is 64. Then for every 64 into 4, I am assuming it's somewhere around 256, the gradient accumulation happens, right? I don't want to have such a larger batch. So let me say just don't use gradient accumulation for every batch back propagate. And I'm saying that use mixed precision, that is your model is going to be in float 16 for most of the layers, and for some layers like batch norm it's not going to be. Okay, that's not actually a pure float 16, it's something called mixed precision. That's why, because we use a combination of float 16 and float 32, and we are saying don't train on the complete data set because the demo I wanted to run very quickly. So I'm saying just use 20%. And we're saying run it for 2 epochs. Okay, and whatever arguments you want to change, you can change it here. And now say run. Okay, now what you can do is you can just click this link and it will take you to a nice dashboard with all the experiments. I'm assuming my net is slow here. Okay, no metrics logged. Let's wait for some of the metrics to be captured. So if you want the train loss to be captured, you can add it in the train epoch. So just like how we did for validation epoch, you can do for the training step also. You can just have a train loss added. So at the end of every training epoch, there is some log that is being captured. So let's look here, let's refresh it. And now let's say we can see the validation loss, validation ROC score, how many epochs it has run, and all the other different things, right? So now we're ready to run more experiments. You should be able to use mixed precision. You should be able to use gradient accumulation. You can use different loss functions. And what else? Go ahead, try running more experiments and see if you can climb on the leaderboard on Kaggle. Or if you're not doing the competition, you can probably apply all of these tricks on keeping your Pytorch code in a very clean fashion. If you see here, there's very little boiler code. All Pytorch Lightning is doing is asking us to structure the code in a particular way, and it takes care of a lot of boilerplate code. I'll not say boilerplate code, but things like how do you push to device, call item, and a lot of things. Like now look at the code that we have created here and go to the Kaggle kernel and look at the code. We find the Pytorch Lightning code to be a lot more simpler, right? Thank you guys. That's it for today. If you like this video, please hit the like button and subscribe to our channel. If you want us to look into some new topics other than the course, please write down in the comments. We will be happy to share our knowledge on those topics. Thank you guys. Bye bye.